All right, hello everybody. The title of this presentation is extent of desmoplasia useful in lung cancer prognosis? My name is John Metelsky, my supervisor is Melania Pintilli, and the practicum site is Princess Margaret Cancer Center. Okay, what is cancer? Cancer is unregulated cell growth. It's the leading cause of death in Canada. Lung cancer is fairly prevalent and is very lethal. Desmoplasia associated with lung cancer is the growth of connective tissue that goes along with the tumor. So it's sort of like you could think about it as the scaffolding that allows the tumor to grow and flourish. So gene expression changes in desmoplastic tissue have been shown to have prognostic value. If a person has cancer and they're expressing these genes, it's possible to use that to make predictions about how long they're expected to live. The question is, does extent factor into that? Here's a visual of low versus high desmoplasia. So this is what the pathologist, for example, would look at these microscopy sections and make this determination. This is an example of just how sort of the data appear and the statistical question that it leads to. So suppose you have gene A, this would be the expression level for each of the people in each of the patients in the study, and likewise for the high desmoplasia group. So the statistical question is, are these the same thing? Is there any statistical difference? So the real purpose of doing this is to determine if a relationship exists between extent of desmoplasia and expression level of signature genes. And the purpose of doing that is to improve the prognostic model by including extent information, and thirdly, to validate extent as an easier, less expensive alternative to genetic analysis for prognosis. So if you can establish the relationship between extent and gene expression, then depending on what situation you're in, you can use one in place of the other, but you'd have to establish that relationship. So this requires a team effort on the part of many people, the molecular biologists to actually perform the genetic experiment. The bioinformatician is pre-processing the data, doing normalizations, making everything reasonable for analysis by the biostatistician, and the clinician to find translational relevance, like how is it that the results of the experiment can be put into use in practice. So to formalize the statistical question, is there a difference in the level of gene expression for any of the 18 signature genes between groups classified by extent of desmoplasia as either high or low? So if you want to answer this question, there's a lot of possibilities, a lot of tools in our toolkit. But the major considerations are that we have small sample sizes and non-normal data. So what I've shown here are histograms for 9 of the data vectors. I selected them completely randomly using R from the data frame. And on visually inspecting these, it doesn't seem as though the data are normal. I mean, perhaps there's just not enough data, but in any case, we want to take an agnostic sort of approach and say, I'm not going to assume that these are normal. For this reason, we decided to employ the Mann-Whitney U-test for independent samples. This is a non-parametric technique, and it's pretty cool. I'm going to explain how it works now. So the Mann-Whitney U-test considers how data from two groups rank without making any distributional assumptions. So let's imagine you have two data vectors, x and y, each containing two data, and there are no ties. It's continuous data. So there are 6 possible configurations of x and y on a number line. So imagine you took like two pennies and 2 dimes and put them in a bag and shook it up and laid them out in a line. There's 6 possible ways that the objects could sit. And so the way that you get your test statistic, in this case I'm calling it, it's called the U statistic, is you would take your sample and you would say, okay, for each y, how many x's is it outranking? So in this case, you would look at this first y and you would say, well, there's 2 x's that it's outranking, and you would take the second y and there are 2 x's that it's outranking. So the U statistic for this sample is 4. And so it goes for the other samples. Now we can see that there were 5 total possible outcomes, 0, 1, 2, 3, and 4, and that each of these occurs once, except for 2, which occurs twice. So this is suggestive of the discrete distribution that I have pictured here. Now what you want to note is that this distribution is symmetric and it's unimodal. So do we all have a favorite distribution that is symmetric and unimodal in mind that this might converge to? Well, the answer is it is approximately asymptotic to a normal distribution. So this normal distribution that it approaches has calculable parameters and is the basis for inference using the Mann-Whitney-U procedure. So here I have pictured a simulation, 10,000 replicates of 12 and 13 data in each vector. From that, the U statistic was calculated in a very similar manner to that which was done here. And then a histogram has been created from the 10,000 replicates, and as we can see, it is very close to normal looking, and the superimposed curve here is the one that is calculated using these parameter formulas. So just to show like the really cool thing about Mann-Whitney-U is that this the normality of this U statistic does not depend on the underlying distributions. So you can see here I used chi-squared, here I used uniform, here I used t-distribution, and in each case you get a very good approximation by this normal curve. Okay, so back to the study at hand. These are the statistical results. I've displayed in this table the 5 lowest p-values, and as you can see, none of them is at or below 0.05. So my conclusion is that at alpha equals 0.05, there was no statistically significant difference in the expression of any of the 18 genes. So what can we consider? Where can we go from here? One question is like, how surprising is this really? You know, the assumption might be, well, you've got higher desmoplasia, so you should have higher gene expression of the desmoplasia genes. Okay, well, it might be the case that once a cell has become cancerous, once a fibroblast has become cancerous, you know, maybe it's sort of more of an on-off thing, and the high versus low desmoplasia has more to do with the number of such cells that have become cancerous, as opposed to how much, how high the cancerous gene expression level is. An important correlation structure may exist in the gene expression. So in my analysis, I took each gene separately and looked at it, which is fine and good, but you know, maybe there are correlations in how they're expressed between the high and low groups that I didn't address. That's something I'm going to be looking at next semester. Is the high and low dichotomization of extent appropriate? You know, you could imagine that the pathologist has this task of making this classification, but certainly the you know, the tissues exist on more or less a continuum, and at some point the pathologist has to draw the line and say this one is high, this one is low. You know, maybe that human error introduced in doing that is important. Are these genes the best candidates for the desmoplasia signature? Well, that's a good question. It ends up that on talking with the principal investigator, they've actually come up with like now a new set of genes that they think is like the best like biosignature for desmoplasia. Another question is how much power was lost by not using t-tests? And I'll address this last question here. I did a simulation, and I just want to draw your attention to this portion of the simulation because it's the most relevant to the experiment at hand. The sample sizes were the same as in the experiment. On 10,000 replications, we see that for normal generating distributions, the t-test had a power edge over the Mann-Whitney-U test. For non-normal generating distributions, the Mann-Whitney test had an edge in terms of power over the t-test. So just to summarize that, when the data were normal, we gain 4% power using a t-test, but when they're not normal, we gain 10% power using Mann-Whitney-U. So in hindsight, since the data in the desmoplasia experiment did not appear to be normal, the Mann-Whitney-U was probably a good choice. Okay, some non-statistical results and things I learned from doing the placement so far. A lot of work goes into even a very simple statistical analysis. So between, cleaning the data from this spreadsheet form into the more usable form in R, all of the research and preparation that goes into doing a presentation like this, it's just caused me to realize even this was a very simple analysis. It was basically just like a t-test or a u-test on two vectors done 18 times. So even in this very simple analysis, it was like a lot of work. Attention to detail is crucial, how you're naming your variables in R, where you're storing your files. These things really matter at the end of the day in terms of efficiency. And lastly, I've learned that I find biostatistics to be a vitally engaging pursuit. And by that I mean there's good alignment between doing good and doing well. And what I mean by that is, in the workplace, doing what I'm asked to do actually feels good, and am engaging my intellect, and I'm doing something that I feel is productive for myself and for society. And so for that reason, I'm quite pleased so far with my choice to pursue biostatistics. I'd like to give a special thanks to my supervisor, Melania Pintilli, and to all of you for having been a great audience. Okay, thank you very much.